Okay, so let me start this lecture. For this one, I will try to specifically give you the fact that we can go from optimal control dynamic programming principle to show that the value function is a solution to, it's a viscosity solution to the corresponding Hamilton-Jacobi equation. Um, um, to make sure that everything is in a good order, let me briefly recall the setting so that like we are on the same page, and also so that this video lecture can be viewed as some sort of independent lecture of interest. Okay, so let me recall quickly the setting. I'm gonna write here. So the setting is that we have the control set. V is the control set. This is typically a compact metric space. Okay, it can be finite, it can be infinite, but compact metric space. And we have a given vector field, B mapping from Rn cross V to Rn is a given vector field that satisfies the fact that which is bounded, continuous, and Lipschitz in the spatial variable in x. That is, we have bx1 v minus bx2 v less than a universal constant times x1 minus x2 for any x1, x2, and v. And I have a cost function mapping from Rn cross V to R is a given cost function that is also bounded, continuous, and Lipschitz in X. That is again fx1 v minus fx2 v is less than or equal to c times x1 minus x2. Okay, so that's the setting. For a control, I mean that this is denoted by a control. That is a v is a function from 0 infinity to the target space, which is a control set, is a measurable function. So it's called a control. Okay, this is what you can control, and lambda is a given constant, positive constant. Yeah, so those are our control and a fixed constant. And again, I mean, we have already described this, but I'm just recalling it, that corresponding to each control, right? You have, for each of the control V, we have a corresponding part of an agent or a particle or a person that following the ODE, that is, you have Y represents for the position at time t, Y prime, Y prime of this equals to the vector field B of Yx at t and vt for any t greater than 0, and at the origin, at the beginning, sorry, you are starting at x. So again, you start at x, and the vector field drives you going around, circulating around. This is your position t, and your cost functional for this control, starting at a given point x. For each of the point, the control is different. The part is going to be different, and for each of the given point of n, a given control v, The cost functional is a infinite integral. This is infinite horizon, e to the minus lambda s f y x s p s ds. Okay. And again, we would define the minimum value function, or simply just value function, to be u of x is just mean of all possible control of the cost functional. Okay. So that's just the basic setting. We define the value function to be this, and again, that remember that that for each of the beginning point x, the dynamics are complicated. And by define the value function, if we just look at the value function, we essentially ignore the dynamic. We just look at the value function. And the theorem that finally we're going to prove for today in this lecture is that we're going to prove that u defined as the value function is the unique viscosity solution to the static problem with the discount factor lambda coming into place, lambda ux plus h of x dux equal to 0 in Rn. Okay, so that's the very nice static Hamilton-Jacobi equation, in which I have where h of x p is the supremum of v in v of minus dxv dot with p. B is a vector, so dot with p gives you a number minus fxv. We take sub over all vector v in v. I already explained in class earlier the properties of h and stuff like that. We can ignore them for now, or you can also just view it as, you know, h is defined like this without referring back. And to prove this theorem, we already explained that we're gonna use the proposition, which is the so-called dynamic programming principle. Dynamic programming principle tells you that, you know, in order for your control to be optimal, it has to be optimal all the ways, right? So for example, when we write down, dynamic programming principle just says that for h fixed t greater than 0, if I am optimal from time 0 to infinity, then meaning that I'm optimal from time 0 to t and t to infinity all the way. That is, I can write ux equal to infimum of among all control. Instead of going to infinity, I can just go from 0 to t, any fixed t of the cost f yx with the control s. I think I forgot the e to the minus. So I don't need to go to infinity, but I just need to go to some fixed time. But I'm optimal from that 0 to that fixed time, and also I'm optimal along the way. Afterwards, that means that I can plug in the value at the time I stop, which is e to the minus lambda t, and the position. There are different ways to interpret this, but as I said, I mean, one simple way is to say that you go from time 0 to t, right? And then from time t to sometime later, you also need to be optimal. When you glue the two things together, it's optimal, because if the later part were not optimal, let's say that if for the later part you can go in some other manner that is better, then instead you can go in this part that is going to be cheaper than the purple one, right? So that means that the purple one has to be optimal. Okay, so let's use this dynamic programming principle to prove the theorem. And the idea I want to tell you, the key idea of how to go from DPP to the Hamilton-Jacobi equation is essentially we're gonna let t goes to 0 in the DPP and use the fundamental theorem of calculus to get to derivatives. You can view of this one as a way to go from certain sort of semi-group theory. When you let t goes to 0, you find the generator, and this is essentially the same. And as I explained already a little bit in class, we can do this one in a formal manner. So let me give you first a formal heuristic proof first, and then we can see how do we go from heuristic to rigorous proof. Okay, so we will prove it in two ways. Let me copy this one. So we have, this is our dynamic programming principle. So the first direction is sort of like, instead of thinking about any complicated control, we can think of our control as just a fixed control. Okay, so I don't change the control, just fix it to be a value in V. Okay, and let's write yx V to be just yx for simplicity. Then for each of this simple control, we have, because the right hand side is supremum, right? So I would have ux is less than a particular choice of my control. Okay. And now the idea is simple. I want to let t goes to infinite to 0, sorry, and then I want to use fundamental theorem of calculus, or use certain differentiation rules to get the result, right? I see the integral from 0 to t will go to 0, so that means that I should kind of average things out. I should divide everything by t and take the limit, right? So that's exactly what I'm going to do. So this implies I can move everything to the let's move everything to the left. So I would have ux minus e to the minus lambda t uyxt divided by t minus 1 over t e to the minus lambda s f yxs ds. ds is less than or equal to 0. Okay, and then I'm gonna take the limit as t goes to 0 plus, and as because it's a heuristic proof, I can assume everything is smooth. That is, I don't have to worry so much about u is not differential and stuff like that. We need to fix it later in a rigorous proof, but I mean, let's do it. So if I assume everything is smooth, the first term is what? If I take limit as t goes to 0 plus of the first term, if you want, you can rewrite it a little bit so that you see it clearer. So I put minus sign here, e to the minus lambda t uyxt minus ux is e to the minus lambda 0 u of yx at 0, right? Because that's the starting point, divided by t. And you can see that this is nothing but minus d over dt of e to the minus lambda t u of yxt evaluated at t equal to 0. So basic definition of differentiation. And you can use product rule and chain rule to compute this. If I differentiate in the exponential, I would have minus lambda. So minus and minus cancel. So I have lambda e to the 0 is 1. So u of yx0 is x, lambda u to the x. And then I have minus, again, e to the 0 is 1 to du at yx0 is x dot with yx prime of 0. Okay, yeah, so that's just basic product rule and chain rule. And now I'm using the ODE. This is lambda ux minus dux. Yx prime of 0 is nothing but the vector field at that point, right? So it's bxv. Remember, we choose v to be here to be constant control. That's what we chose, right? So that's that. And the limit of the integral is nothing but the average, right? But as t goes to 0, it becomes simple. What we have, let me just combine everything. I would have lambda ux plus of minus bx v dot with dux. Again, the average of the integral is nothing but the value of fxv. Okay, this is less than or equal to 0. And this is correct for any v, a fixed vector in the set V. Okay, now you can recall that we have h of xp equals to supremum of v in v of minus bxv dot with p minus fxv. Okay, and you recall, you can just think of p as du here. Then you take supremum of over all vector v in v. We get lambda ux plus h of x dux is less than or equal to 0. Okay, so that shows that u is a subsolution. Again, assume that everything is smooth. Okay, so you can see that we start with choosing a constant control for any fixed vector v and v, and we just do the basic rule of computation in calculus. We get to the result. And you can see that also this sort of problem is not symmetric, meaning that we to prove the super solution property, we more or less can't do it in this way. We need to do it differently. So this gives us the subsolution property. Okay, so let's now try the super solution property. Okay, for super solution property, again, this is a heuristic proof. I recall to you here, let me highlight it, that we have the dynamic programming principle. Okay, it's not clear, but supposedly that from this dynamic programming principle, or from the optimal control, the value function, let's assume that I know that there is again, it's heuristic, so let's assume that I know that there is an optimal control. Okay, what do I mean by that? To prove the super solution property, I do it differently. I assume, and in the rigorous proof, I will need to do it also differently. There exists an optimal control such that for this optimal control, it does minimize the cost functional, right? Or in other words, I do have ux equals to integral from 0 to t e to the minus lambda s f of yx v star s v star s ds plus plus e to the minus lambda t u at yx v star t. Okay, so for this optimal control, then everything is optimal, right? So I have equality. Let me highlight it. This thing again, we don't know whether we really have an optimal control or not, but let's suppose so. Then again, you can see what I'm gonna do. I'm gonna go exactly in the same manner to derive the corresponding like inequality, and here I have equality to start with, right? So what again, for simplicity, so let's just write yx with the control v star to be yx, for simplicity. So we just compute. Okay. How do we compute this? Again, move everything to the left. Okay, so let's say that I have e to the minus lambda times 0 u of yx 0 minus e to the minus lambda t u yx at t. Okay, this is a difference in u minus integral from 0 to t e to the minus lambda s f of y x s v star s ds. Okay, this is what we have equals to 0, an equality. And now here, as I said, I'm using the fundamental theorem in calculus. This equals to what? This equals to minus the integral from 0 to t d over ds of e to the minus lambda s u of yx s ds. I'm using exactly just the fundamental theorem calculus, minus 0 to t e to the minus lambda s f yx s v star of s ds equals 0. Okay. And let's expand this one out. This means that I have integral 0 to t. Again, I'm doing exactly the earlier thing, using product rule and chain rule. The first thing I would have is lambda u yxs minus du yxs dot with yxs. Okay, and minus f combined together, f of yxs v star of s. Okay, all multiply with e to the minus lambda s ds equal to 0. Okay, now let's divide everything by t. Lambda u yxs minus, let's write down what is yx prime. Yx prime of s is du yxs dot with b yxs v star of s. Okay, I'm just rewriting that yx prime is this vector field minus f yxs v star of s e to the minus lambda s ds equal to 0. Okay, now what I'm gonna use here is that I'm gonna use right away an inequality. I'm using the fact that the Hamiltonian is defined to be supremum among all vector v, right? So I'm just thinking of v star as one vector. So by definition, this is less than equals to h evaluated at yx of s du yx of s. Okay. Again, I'm using the fact here is that for a particular choice of v, I have h of xp is supremum among v of minus bxv dot with p minus fxv. This must be greater than or equals to any particular choice of v. In this case, v is v star of s. That's just a basic fact. Yeah, and we are in business. We have 1 over t integral from 0 to t lambda u yxs plus h of yxs du of yxs, ds is greater than equal to 0. And again, you take the average, you let t goes to 0. Everything is continuous, everything is supposed to be smooth enough for you and stuff like that. So we recover exactly that that ux, lambda ux plus h of x dux is greater than equal to 0, and we are done. Okay, so you see that to prove one-sided inequality, I chose V to be just basic constant constant control to get the subsolution property, and for the other I mean, here in this heuristic proof, I'm using the optimal control, I mean unoptimal control to get the other side, that inequality. So now let's do rigorous proof. Okay, so wait. It turns out that it's not too hard to go from heuristic proof to rigorous proof. Okay, you can see that here what I'm using in this heuristic proof is that the basic point I'm using here is that I'm using u is sort of nice and differentiable, stuff like that. I can't not do that in the rigorous proof because we typically only have u is bounded uniformly continuous or Holder or Lipschitz. It's not differentiable in general, but as we learned, we can always pass the differentiability of u to the test function, right? So that's exactly going to be the trick we are using. You will see that it's going exactly in this way. Okay, so so let me just write down very quickly the first part, which is a subsolution proof. Okay, how do we do the subsolution proof? You take the function u, right? Again, it might not be smooth. You touch it from above by any possible test function at any possible point. So let's say you touch it from above. This is not smooth. So you touch it from above by a smooth function. Let's say you're touching at x0, right? So phi smooth touching you from below at x, so from above at x0. Again, we want to show that lambda ux0, and because they touch is equal to phi of x0 plus h of x0, the phi of x0 is less than equal to 0. And again, this equals to phi of x0 because they touch. And if you write down the dynamic programming principle, you will see, right? So I'm doing exactly the same like earlier. Maybe let me even copy. Let's see, what can I copy? Yeah, actually I can copy it and I will replace it for you. You can see. Let's see. Okay, let me copy this part. So what I'm going to do is that basically I'm just going to modify things a little bit and you will see. Follow nicely. Okay. A little bit slow. Okay, I think I'm good. All right. So I'm copying everything. So I tag uh, okay, I'm gonna put x0. It just messing things up a little bit. Okay. Let me change x0 to x now so that it's actually easier. I don't have to change things a lot. So I'm assuming that touches as x. Okay. So things touches at this point, which is x. we need to prove this at the point X. Okay. So I'm writing down from the dynamic programming principle, we still have this. So this is from, oops. This is from dynamic programming principle that when we choose any possible control, in this case, we choose constant control, then we have that U is less than the right-hand side, right? Again, I cannot deal with U. So what I'm gonna do now is that I'm gonna switch from U to the test function, and you can see that it's going just very nicely here. How? Well, you can see that I have Ux is what? Ux equals to phi of X. Okay, so it will be replaced by phi of X. Oops. U to the U of Y-X is T, any U, you can see that phi touches U from above here, right? So U at any other value is less than equals to phi at that value. So you see, I'm naturally, this is less than equals to phi of Y-X at T. So I'm naturally passing all the value of U to the value of phi already, right? So it's simple. Now, that means that I'm more or less done with the subsolution test, right? Because I have replaced U by phi. Okay, so that means that in the inequality below here, instead of using U, I'm just replacing U by phi. So I would have phi of X minus e to the minus lambda t phi of Y-X-T divided by T minus that is less than equal to 0. So very simple. We are passing from U to phi in this basic step. And now the calculation is being done for phi. And remember that we have phi is a smooth test function. Everything is nice. Okay. So you can see that we are now doing the calculus rule for phi. So I would have phi here by using the chain rule and product rule is d over dt of this product at t equals to 0. This equals to everything of U is being replaced by phi lambda times phi x minus d phi x dot with yx prime at 0, which is equals to lambda phi x minus d phi x dot with this vector phi. Again, is constant control is v. Okay, so then again I would replace now U by phi lambda phi x minus bxv d phi x minus fxv is less than equal to 0 for all v. And again, phi is a smooth test function. You take sub over v in v, you arrive at the result, which is lambda phi x plus h of x d phi x is less than equal to 0. Done. So very simple. You can see that it's going essentially naturally from the heuristic proof, right? So the subsolution test is done. Okay, the second part. What color did I use? Okay, the second part now is the super solution test. Again, the picture is that this is U is being touched from below at a value X. Again, I don't want to use X naught because it complicates our ODE and stuff, the notation. So it being touched from below by a function C smooth at X. And we want to show that C of okay, let me lambda U of X plus H of X dc of X is greater than equal to 0. And let me recall again, U of X equal to C of X because they touch each other at this point. Here I need to be a little bit more careful because, as I said, let me recall from the beginning here. The value function or minimum value function U is mean over all control. The control in general quite bad. They are only measurable. So I'm actually not sure if I have an optimal control or not, right? So I need to be careful there. In the heuristic proof, I was telling you that if I have an optimal control, I can do it, naturally. But now in the rigorous proof, let me be not that careless. Let me not assuming that I have an optimal control. So what I mean is that I'm gonna deal exactly with the DPP formulation, and I pass the limit there. Okay, so let me write it down. Okay, so what is the DPP formulation from here? Okay, let me recall. I have DPP formulation, Ux equals to infimum over all control of integral from 0 to t e to the minus lambda s f of yx control s vs ds plus e to the minus lambda t. You evaluated at that endpoint, which is yx of the control at t. Okay, so I'm gonna basically pass from u to the test function in this DPP now, and then I'm gonna sort of like let t goes to 0 with this test function, because the test function itself is smooth, as I explained. Okay, so what do we have again? We recall that ux equal to c of x here. Okay, and we also recall that at any other point, u of yx is v at t is greater than equals to, because u is above c, right? So greater than equal to c at this point. Okay, so I'm replacing u by c now by smooth test function, and now I'm playing around with this test function only. Okay, now this is greater than equals to that. So what do I mean? Let me write carefully here. So that means that I have c of x is greater than equals to infimum e to the minus lambda s f yx s ds ds plus e to the minus lambda t of the c yx. Again, I am not assuming that I have an optimal control now. So what I'm going to do is I'm just keep that whole infimum formulation. I move one, let's move both of them to the left-hand side and see. So this is equivalent to move the thing to the right-hand side. Okay, move it like this. So move minus is greater than or equal to 0. Okay. And then minus of inf is sup, right? So is supremum of the control. I'm putting the minus inside, and I'm also putting c inside. So I have c of x being inside. You c of x is independent of control. I put it inside. It's just a constant with respect to the control. X is a fixed point now. Minus e to the minus lambda t c y x minus yes, greater equal to 0. Okay. And again, I'm keeping the sup over the control because I want to be careful. Still, I can just write out the first one by basic rule of fundamental theorem of calculus, right? So this equals to integral from 0 to t minus d over ds e to the minus lambda s c of yx s ds. Okay. Minus and it takes a lot of time to write a lot of indices around. Okay, sub over all control is greater than or equals to 0, right? And again, expand everything out. By now I don't have to to say it again, right? So it's just calculus computation here. You have integral from 0 to t. Okay, so now let's divide everything by t. It's the same. E to the minus lambda s is a constant common term. Lambda pops out when you differentiate in this exponential. Differentiate in the c term, you have a minus dc s dot with yx v prime at s minus f yx v s vs everything ds is greater or equal to 0. Okay, and again we are using now the fact that this is the vector field b of yx vs, and then we are using this fact that this whole term is less than equals to h evaluated at the location yx vs. The dc, again, c is a smooth test function. I can do this. Okay, so same thing, right? We are using h is a supremum, and hence it's greater than equals to any individual v chosen, in this case vs. So I have that. So then I can say this is equivalent to supremum, wait, not equivalent, imply sub of vs 1 over t e to the minus lambda s lambda c of yx s plus the Hamiltonian s dc yx s ds is greater or equal to 0. Okay, now we need to be a little bit careful here to conclude, but every element is on the table. What we need to be careful here in order to conclude is that you can say, wait, but what happened if my control is getting crazier and crazier, and the change in the y in the position is very a lot, right? Then I cannot take the average of this integral. But remember that so there's recall this recall that again yx prime of s is this vector field which is bounded vs, and we have proved that for this ODE, the key thing that we have we proved in class, but you can check this one very simply, is that yx t minus yx s is less than or equals to a universal constant times t minus s. So that means that, you know, the solution to the ODE doesn't deviate so much from the first position if t is small, right? So that means that this implies that for t small, you know, you can see that yx s minus yx v0, which is x, right? The original point is less than or equal to c times s less than or equal to c times t, which is small. So when you let t goes to 0, you have continuity in everything, right? So then you let t goes to 0 here. It doesn't matter for whatever control, because again, all controls are in compact set. This is a key. All the values of the control, not all control, all the values of the control in the compact set. So you always have this bound. And hence, when you let t goes to 0, you have the average out, right? Just a basic mean value theorem, whatever. You have lambda c evaluated at yxv as 0, which is x, plus h of x dc of x is greater than or equal to 0. Okay, so we are done. We have the sub and super solution test, and we have shown that so let me conclude it here. Thus we have shown that u defined as the minimum value function, right, is a viscosity solution to the equation h of lambda u plus h of x du equals to 0 in Rn. Okay, we need to do a little bit more. I'll discuss about this, but recall that we have the very important property of H, which is that P maps to H of XP is convex, right? Again, if you want, I can recall the formula here. It's a supremum of a bunch of affine function in P. So is convex in P. We also have checked that they satisfy, I mean, the Hamiltonian satisfy, it's satisfying what? It satisfy structural conditions to have uniqueness of the solution. In other words, we have checked, or you can check it again, that h of xp minus h of xq is less than or equals to constant times p minus q, and h of xp minus h of yp less than or equals to constant times 1 plus length of p x minus y. So we have checked those. So it satisfies the structural assumption for us to have that uniqueness result. So okay, I'm cheating a little bit here, but basically then we can conclude that U is the unique viscosity solution, right, to the equation. Okay, so now let me end by making some remarks. Okay, so as I said, I am still cheating a little bit about the problem here because I have not said so much about the regularity of U. I mean, but remember that in class we did give some example that said, okay, I should note that by the formula above, h of xp is supremum v in v minus bx minus fxv is convex in P. Okay, I'm repeating myself. But it may or may not be coercive in P, right? So H may or may not be coercive in P. Again, here by coercive in P, I mean the limit as the length of P goes to infinity, infimum over x of h of xp equals to plus infinity, right? It could be coercive or not coercive in P. We already gave 2 examples or 3 examples in class in earlier that it could go either way, right? You can think about example. Let me recall quickly. V could be, if V, I take V is the unit ball, F depends only on X, and Bxv is V, then you can compute that h of xp equals to supremum of all v length less than or equals to 1 of minus v dot p minus fx. This equals to p minus f of x. So if f is bounded uniformly continuous, and this is coercive in P, but it could go either the other way, right? If you take v is equals to only 2 vectors minus e1 and e1, in the canonical basis of Rn, and same for F and V, F and B, then you can compute easily that h of xp is only equals to p1 minus f of x, and this is not coercive if the dimension is greater than 1, right? Because if you take p2 goes to infinity, for example, then this Hamiltonian doesn't go to infinity. Why did I mention about this? Because we did prove earlier that for this sort of Hamiltonian, and if we have h is coercive, then you can see that u is bounded. If u is bounded, then this is bounded, and by coercivity, you have du is bounded, meaning that u is Lipschitz. So you have nice regularity of u, right? But again, in the second example, that u might not, h might not be coercive, and when h might not be coercive, then we cannot conclude that u is Lipschitz, right? So this is a very subtle point saying that in this sort of optimal control manner, we might not always have coercivity of the Hamiltonian, but still we have uniqueness of this viscosity solution, and the value function again might not be Lipschitz in general. Okay, so let me think. Okay, maybe let me write down this result, and then I'll leave it for later. So where I am. Okay, so as I said, I will write out this result, and then I will let me think. Maybe I'll give you to you as an exercise, which is not so hard, but as I said, you can see easily from this formulation that what you can see easily from this formulation is the fact that u is bounded. Okay, so you can see the fact that like earlier, right? So okay, maybe you can see that lambda times u in L infinity is bounded by the h of x 0 in L infinity of x Rn. So that means that you have a lambda u in L infinity is bounded by c. Okay, the boundedness of that is not a problem, but again, we might not have that u is Lipschitz in general. So here's an interesting result. Again, I will just write it down here. Maybe I'll give it to you as an exercise. So this is theorem 2.9 in the textbook, which is rather interesting. Is that sometimes for very big lambda, we do have that u is Lipschitz, but when lambda is small enough, then we only have that u is Holder continuous. Okay, so the theorem says the following: you set lambda 0 is the L infinity norm of the gradient of x in B, or the you can say it's the Lipschitz constant in x variable, infinity of Rn cross V, which is a Lipschitz constant. Okay, so you can use basic ODE theory to prove the following. Then the following holds. The first thing is that if you have lambda is greater than lambda 0, meaning lambda is large enough, right, greater than this constant, then you would have u is in Lipschitz of Rn. So it's Lipschitz, and as we already showed, that it's bounded. So it's bounded uniformly continuous in Rn. So this is the first case scenario. It's Lipschitz, okay? But we need to require lambda is large. Recall that this is sort of like sharing certain same philosophy with the first existing theorem of elliptic equation that we often need to require lambda large to apply the Lax-Milgram theorem. It's not exactly, but I mean, so the second thing is that if lambda equals to this lambda naught, this threshold, then we would have U is in C0 alpha of Rn for any 0 less than alpha less than 1. So it's nearly Lipschitz. It's Holder for any possible Holder constant. And the third one is that if 0 less than lambda naught, then we would have U is in C0 with a Holder constant, Holder exponent lambda over lambda 0 of Rn. Okay, so in this case, alpha is lambda over lambda 0 less than 1 greater than 0. Okay, so in any case, clearly that U is bounded uniformly continuous and is the unique viscosity solution. What is striking or remarkable here is that, again, the Hamiltonian might not be coercive, and hence we do not always expect that our solution is Lipschitz, but still it's nice, right? I mean, it's Lipschitz if lambda is large, or else it's Holder, which is good. Okay, so let me stop the lecture here. How do I stop?